Alright everybody, so in this video I'd like to talk to you about the concept of reaction spontaneity. Alright, and of course if you remember what a spontaneous reaction is, a spontaneous reaction is one that will occur by itself without any needed input to actually occur. A non-spontaneous reaction is one that will need constant help to actually occur. Alright, so if you think about spontaneous in terms of processes rather than actual chemical reactions, alright, if you were to say here's a hill, and here's a ball, and here is you. Once you give that ball a push, it's going to roll all the way down by itself. It doesn't need any extra help. It needs a little bit of a kick to begin with, so you kick it off and it goes all the way down. It rolls down spontaneously, alright? Now on the other hand, if somebody else was down at the bottom, okay, this guy's kind of giant, but anyway, if this guy was down at the bottom here and was going to say, well, that ball's going to roll back up the hill, then of course it won't. It's going to need constant help from somebody pushing it up. Alright, so rolling down would be spontaneous, rolling back up, which of course wouldn't happen without you pushing it, would be non-spontaneous. Alright, so let's talk about spontaneity in terms of chemical reactions. Let me give you a little bit of history first. Historically, reaction spontaneity was linked to reaction enthalpy, the enthalpy change for a reaction, so the delta H here, which from what you've seen before can either be positive or negative. What most people thought was if a reaction was exothermic, thus had a negative enthalpy change, as is shown by the combustion of methane here. Alright, the delta H for this happens to be essentially very exothermic. It's negative 802 kilojoules. The thinking was that all spontaneous reactions are those that are exothermic. Alright, in other words, those that have a negative enthalpy change. Alright, and this actually at the time seemed to make sense because the vast majority of chemical reactions that people found that were spontaneous happened to be exothermic. It just happened to be that way, and so the common prevailing thought was, well, if what we're seeing is true, then every exothermic reaction must be spontaneous. But it wasn't that much longer until reactions were found that although they happened spontaneously, so they gave it a little bit of a start and then they just carried on by themselves, although they were exothermic, although they were spontaneous, they didn't give out heat in the way an exothermic reaction does. For example, this guy right here, the decomposition of dinitrogen pentoxide. It has an enthalpy change, and actually, you know what, I just need to change something here. I'm just going to add a couple of things. Rxn, because this is the enthalpy of the reaction. The little zero here means this is the standard enthalpy change. Alright, so we're going to say the same thing here. Measured under standard conditions. 1 atmosphere to 298 Kelvin. Sorry, 273 Kelvin, not 298. For this reaction, for the decomposition of dinitrogen pentoxide, what was found was that this actually had the opposite sign for its enthalpy change. So this had a positive enthalpy change, so therefore it was endothermic, and yet it still ran without any extra help once it got started. So then people were thinking, well, that doesn't make any sense, because if we're saying that all reactions that are exothermic are spontaneous, then either our hypothesis is wrong or something very odd is going on. And what it turned out was it wasn't that there's anything weird going on, it's just that the picture about reaction spontaneity at that point wasn't complete. And there are a couple of other things to consider that when this was first formulated were not taken into account. And we'll talk about one of them right now. One of those issues is the effect of temperature. Alright? Reaction spontaneity actually is temperature dependent. Let me just give you two examples. Let's look at, for example, the freezing of water. All right. So let's say we take some liquid water and we freeze it. You can measure the enthalpy change for this, as you can for really any chemical process that that you can monitor. And then down here, I'm going to do exactly the same thing, but the opposite. Okay. So the freezing of water, all right, has an enthalpy of reaction of negative 6.02 kilojoules. All right. The enthalpy of reaction here, which is exactly the opposite, is like so. However, it's important that we understand that this picture is not complete, because from what we're saying here is the freezing of water going from liquid to solid apparently is spontaneous. Well, if you think about it, you know, well, that's not necessarily always true. If I have some liquid water out on the bench top, or you know, out on the table at home, well, this is exothermic. It isn't going to just spontaneously freeze. No, of course it's not. Just as when you have solid ice go into water. Here it says this is exothermic and thus not spontaneous. Well, if I leave out some ice, it is going to melt spontaneously. All right. So the important thing to understand here is the picture's not complete. So I'm just going to add this. We know that according to the numbers here, this is exothermic, and that's fine. Energy is given out when ice melts, when water freezes to ice. That's fine. But it's only spontaneous at a certain temperature. So just think about it for a minute. When or at what temperature would the freezing of water be spontaneous? Well, when you make some ice cubes, you always put them somewhere, and of course that's in the freezer. So this reaction is only spontaneous at temperatures below 0 degrees C. All right. Now, when I look at this guy, endothermic reaction, it's actually rather the opposite. All right. Ice is not going to spontaneously melt to water if it's really cold at these temperatures. It's only going to melt if the temperature is higher, above 0 degrees C. All right. So the important thing is here, and this applies to all reactions, not necessarily these numbers, but reaction spontaneity, at least to do with the enthalpy of reaction, does have a temperature effect. Okay. But the reaction still isn't complete, or the whole understanding of reaction spontaneity still isn't complete, because there's one other thing as well, and it's something that's actually very important. It's something that would allow me to estimate, without looking at this delta H here, by just looking at this reaction, I could tell you that this is probably a spontaneous reaction. All right, and what it's to do with is actually the states involved. All right, I have solid, my dinitrogen pentoxide, and then I have two gases. All right. The thing that we need to concern ourselves with is something called disorder or entropy. All right, entropy given the symbol S, so the entropy change for a reaction will be shown like so. Entropy, as I just said, is a measure of disorder. All right. So the more disorder in your system, the more molecules are spread apart, the more randomly they're moving, the higher the disorder. That's why gases always have a higher disorder than liquids, which have a higher disorder than solids, because solids have very organized particles. Gases, on the other hand, are completely disordered, and there's complete randomness. Okay. So, because of the fact that the entropy of the universe is constantly increasing, as says the second law of thermodynamics, then what that says is a reaction with an increase in entropy should be spontaneous. Okay, Now we can do the entropy change as we can do the change of anything, as the products minus reactants. In this case, it will be the we can look at it in terms of moles of gas to estimate. So 3 moles of gas, 2.5 moles of gas on the product side, 0 moles of gas. So we have a positive entropy change. We have a positive, yeah, that's right, a positive entropy change. So when your entropy change is positive, all right, that means it's more likely to be spontaneous. It doesn't mean it is, it just means it's more likely to be than if you have a negative entropy change. So what we're going to do is we're actually going to combine what we've been talking about with the enthalpy change, what we've just been talking about with the entropy change, and our temperature issue as well. And we're going to tie all this reaction spontaneity business together with one formula. And that formula is for something called Gibbs free energy for reaction, for process, whatever you are studying. In this case, we're looking at a reaction and the system in particular. Gibbs free energy has the symbol G. So change in Gibbs free energy is equal to the change in the enthalpy of the system minus, that's an important thing having that minus sign here, minus the product of the temperature at which the reaction is being run and the entropy change of the system. So this is an important formula right here. This is extremely important, and there are some things that I want to just go through with you, because this reaction, or this equation here, will allow us to tell by looking at some numbers whether the reaction is going to be spontaneous or not. All right. Now the one overall goal that we're looking for, and this does make predicting spontaneity a little bit easier, is the main thing you're looking for is, in order to have a spontaneous reaction, you need a negative Gibbs free energy change. It has to be negative. If it's positive, then that means a non-spontaneous process. All right. So negative means spontaneous. A positive entropy, positive Gibbs free energy change means the reaction is going to be non-spontaneous. And there's one more example as well, and that's when we have, let's say, when we have a delta G of 0. We don't really see this very often, but when we do, what it means is it means a process at equilibrium. But again, most common sorts of processes you'll see will be whether you've got your delta G of less than 0 or delta G of more than 0. Okay? So it turns out that based on the sign and the magnitude of delta H, delta S, and T, you can actually figure out whether it's going to be spontaneous or not. And there is a table here that illustrates the 4 possibilities. So I just want to go through them all in turn. If we look at this first one here, we can have possibly 4 different ways of arranging the respective signs of delta H and delta S. Okay, if we look at the first one, if we have a negative delta H, all right, which suggests a spontaneous reaction but doesn't say that for sure. And also bear in mind, a negative delta H, if we have a negative sign here, that's going to more than likely give us a negative sign here. So a negative sign is what we want in our delta H for spontaneity. But then let's look at the delta S as well. We said before we want a positive entropy change, a positive value for delta S. Because a positive sign here multiplied by the minus sign, of course, gives us the minus. So we have minus sign here and a minus sign here. What that means is no matter what our numbers are, our delta G is always going to be negative, which is exactly what we want. So when you have an exothermic reaction with a positive entropy change, it doesn't matter what your temperature is. Your temperature can be low or high, whatever. Because of the 2 signs here, negative and negative, at whatever temperature you run, the reaction is always going to be spontaneous, and that's an important thing to understand. So when we switch our signs and look at the plus and the minus here, a positive delta H means endothermic, positive delta H means this may have a positive sign too, which is not what we want. A negative delta S, again, suggests not spontaneous. And when you think about signs, negative times a negative is a positive. So you've got positive all this and positive here. That's going to give a positive delta G, again, irrespective of the temperature. All right. So for the first one, the first situation, we have always spontaneous, no matter what the temperature is. The second situation, we have a reaction that's always non-spontaneous, again, irrespective of what the temperature is. But when we get to the last two, 3 and 4 here, what we find is that the signs for the delta H and delta S give opposite signs here. If we have an exothermic reaction with a decrease in entropy, for example, if we have this, and we have a negative value for our delta H. Alright, I'm going to say that's one piece here. And then we have a negative T delta S. Alright, if this delta S is negative, then that times that is a positive. So what that means overall is we have a negative combining with a positive. So we have a positive combining with a negative. And so the thing that's important then is, well, which of these is bigger in magnitude? All right. Is the delta H bigger in magnitude, or is the T delta S bigger in magnitude? Because that's going to determine whether it's spontaneous or not. And that's where temperature can be important. All right. In order for my reaction to be spontaneous here, I want my delta H to be very large, or my magnitude of this to be bigger than this. So therefore, do I want a high temperature or a low temperature for this to be spontaneous? Well, in this case, I'd like a low temperature. Alright, so I want my temperature to be low. If my temperature is low, then my T delta S is low. Therefore, the magnitude of this is higher than this, and the reaction is spontaneous overall. Now, when we go to the last one, alright, so we have the same thing, but in this case we have a positive enthalpy change, which again is going to tell us initially non-spontaneous. And then we have our T delta S. Alright, so I'll put that in here. If our T delta S is positive, multiplying by the negative sign here, that ends up being negative. So we have the same issue that we had before. We have the opposite signs fighting it out. And in this case, we want the T delta S to be bigger in magnitude than we want the delta H, if we're looking for a spontaneous reaction. So in this case, we want our temperature to be large. If we have a large temperature, then T delta S is larger, so negative T delta S is bigger in magnitude than the positive delta H. So that makes for a bigger negative number, so the delta G, the free energy change, is negative. Alright, and this table just illustrates exactly what we've been saying. Alright. So, for the case number 1, it doesn't matter what your temperature is, it's spontaneous at low and at high temperature. For case number 2, opposite of case number 1, low or high temperature, it doesn't matter, the reaction is always going to be non-spontaneous. For case number 3, which we illustrated here, the reaction is spontaneous at low temperature, when this temperature is low, when this value of T is low, so the negative delta H wins out. And then for the last one, this is spontaneous at a high temperature because the high value of T gives a high value of T delta S, which makes this negative piece bigger than the positive piece. Alright? So it's important that you guys understand exactly what's happening there, that spontaneity in a reaction can be determined by considering the enthalpy change of the reaction, the entropy change of the reaction, and the temperature at which the reaction is run. Alright. Now just one more thing before I go. You can actually figure out free energy, enthalpy, and entropy by using data tables given in the back of your textbook, usually in the appendix or somewhere like that. There'll be big tables of free energy, standard free energy values for compounds. There are standard heats of formation for compounds made from their elements in their standard states, and there are also tables of entropy values for species as well. And you just apply exactly the same rule each time. It's if we were to figure out, or if we were to be asked to calculate the free energy change for example, this reaction here using appendix whatever it may be. Well, all we'd say is, well, if I'm looking for my free energy change, then I can say my free energy change is going to be equal to the free energy of my products, because remember, change is always products minus reactants, minus the free energy of my reactants. Now, of course, I'm adding all these together, so these are all sums. Alright, so the sum of the free energies of my products minus the sum of the free energies of my reactants. And it's exactly the same, say, for entropy. If you want to figure out the entropy change for a particular process, it's just the sum of the standard entropy values of the products minus the sum of the standard entropy values of the reactants. Alright, so if we were to do it for this guy, we would figure out, okay, let's find the value for the free energy change for this and for the free energy change of this. And we're talking about free energy of formation, the free energy of formation of CO2, the free energy of formation of H2O, multiplied by 2 for the water because there's 2 of those. So it would be these two, or all these added together, minus the free energy of formation of O2, 2 of those, plus the free energy of formation of methane. Alright? And whether that would be negative or positive would, well, you just figure it out and get the answer. Okay. That, in effect, is a little bit about reaction spontaneity, so hopefully that has helped somewhat. Thank you.